Greetings, Sainsman. We have lesson 9.1 to the Pythagorean theorem. This is going to be a little bit of a proof for you guys, and then I'll go through just a couple examples of things that we're going to see in class. And this is a fun proof. It's not a two-column proof. It's more algebraic and graphical, but again, kind of getting away from just the trust me, bro nature of things that you guys have been taught that there's this theorem that a squared plus b squared is equal to c squared. And you're taught this um, all the way back during, actually, it's a seventh grade standard. And then one thing that I want to but really make sure that we establish, and what this really means is that the sum of these legs, A and B, are going to be equal to squared. It's going to be equal to the hypotenuse, the longest leg, which is opposite the right angle of a triangle, squared. What this doesn't mean is that a squared plus b squared does not equal a plus b squared. Okay, this is a huge misconception. Now, some of you guys have seen this before, what this is. This is a binomial square. It is an entirely different thing. So, showing you guys what that is. So, let me go ahead and construct two identical squares real quick for you guys. And we're going to go through a proof as to why the Pythagorean theorem is what it is and how they even came, one of the ways they came up with it. I can do three or four, not really six or seven, just three or four Pythagorean theorem proofs. But these are the ones that this is the one I'm going to make sure that we utilize together. Okay. So I'm going to subdivide, and I've got these two squares. I'm going to call this guy figure 1 because I'm going to subdivide it and kind of break it up. And this guy is going to be called figure 2. Okay. In subdividing this, I'm going to do it in the same way that I'm going to just have some length that's going to be about a quarter of the square. And this here, I'm going to mark off about a quarter of the square. Same thing on this side, identically, about a quarter of the square and about a quarter of the square. And the length on this side, right? This has been subdivided. We're going to say that this guy is section A and this is B. And I did this equally where this is both A and B. Okay, and then I'm going to do the same thing. So I think you guys follow along with me. I just have this subdivided, right? So this is like some point, really. But rather than making a point, I'm going to make it a little tick mark to kind of show where I'm going to work from. Okay. Now, figure 1, what I'm going to do is I'm going to create B. So what I'm going to do is I'm going to connect directly to this other side with a vertical line, and then the same thing with a vertical line over here. So that this right down here, in this rectangle, if I were going to take the area, it means I'm going to multiply the side times the side, or the length times the width, right? Which is going to give me A times B. And again, I have that an identical rectangle. Now remember, this length down here is also going to be B. So this is going to be A times B, right? Because this is my length A, my width B. Over here, I've got this little square, right? With side lengths of A. So A times A is A squared. And then right here, this rectangle or this square right here is B times B, which will be B squared. Okay? I'm going to subdivide this guy a little bit differently, where I'm going to similar thing. I'm going to go, rather than straight down, I'm going to have A here, right? And then B here. And the same thing, A here, and then B here. It's the same figure. I still have lengths A and B that are subdivisions in these smaller segments, okay? And then I'm going to connect, watch this, between these, and I'm making some right triangles. And also, potentially, a third side length each time, okay? Now, this little side length here would be side C, right? So if I'm going to take that and I have this side here, and this is going to be C, like, right, side length C. So C times C, my area right here is going to be C squared. And then I'm going to create these little triangles. Now, how do I find the area? Now, remember, this is a right triangle, right? Because it's a square, so there's a right angle at every single vertex. So I'm going to take AB, but remember that for the area of a triangle, it's 1/2 of the base times the height, right? Or in other words, 1/2 of these two side lengths, 1/2 of A times B. And these are all identical triangles, so these are all going to be the same. 1/2 of A times B, 1/2 of A times B, and then this guy down here, 1/2 of A times B. So, one thing I know for sure is that the area of this figure right here, in the area of this figure 2, I, with my software, copied and pasted these. These are identical identical squares. Okay? So identical figures that therefore have identical and equal areas. Now let's create a composite area here. In other words, let's just take a sum of all these little areas that made up figure 1. So we have A squared, we have B squared, we also have AB and AB, which is going to give me 2AB, which is equal to, okay, the sum of all of these, which we have C squared plus all of these little triangles, right? 1/2 of AB plus 1/2 AB plus 1/2 AB plus 1/2 AB. Now, let's do a little bit of algebra now. I have A squared plus B squared plus 2AB, which for the record, let's go back here. Remember when I was talking about A plus B squared? Okay. Well, this is A plus B. This is A plus B for this side. You multiply them times each other. It doesn't equal C squared. It equals A squared plus B squared plus 2AB, which you guys should know because it's a binomial square. A squared plus 2AB plus B squared. Here, let's combine these terms. Okay. All my 1/2 AB, so I have C squared plus 1/2 AB plus 1/2 AB plus 1/2 AB was 2AB. And then I think you guys can probably see at this step right here where this is going to go. If I could actually eliminate this term. If I took away the 2AB from each side, this is going to cancel, which would make this cancel. Oops, that's not 2AB squared. Sorry, this is 2AB. This is going to cancel on this side, leaving me with A squared plus B squared equally. Oh, goodness gracious. How to do that? Scared of this. Oh. Sorry about that, guys. We're at the exciting moment of us completing the proof too, right? Sorry. So we eliminated the 2ABs and we're here with A squared plus B squared now equaling, uh-oh. And then now my pen dies on me. Goodness gracious, guys, I'm a mess. This is tricky. Get this guy working here. There we go. Okay. How anticlimactic. Back to it. A squared plus B squared equaling what's left on the right side, which is C squared, which you guys recognize as this is your Pythagorean theorem. So let's go ahead and use it to solve. I'm going to turn on my little auto shape tool so you guys can get a nice, crisp, clear figure. This is a right triangle. This is a 3. This is an X. This is a 6. This is going to be an important right triangle for us. We're going to solve for X. Okay. Now remember what the Pythagorean theorem says. It says the sum of the legs, A and B. How do you figure out what is A and what's B and what's C? Well, here's what you always figure out. Right here, this right angle. Okay. This will always create C. These other two, because that's the longest leg, or it's the longest side. The other two sides are what are called legs, which are going to be adjacent and include that right angle. So it will be a squared, which is 3 squared, plus x squared, which is b squared, will equal 2, right? Opposite the right angle, c squared, which is 6 squared. And then now we just do a little bit of algebra. 3 squared is 9, plus x squared is equal to 6 squared is 36. Subtract 9 from both sides. So I have x squared is equal to 36 minus 9, which is 27. And then to get x by itself, we're going to take a square root of both sides. Okay? Oops, it's a really sloppy square root. And then square root of x squared is just x. And then now this is not a plus minus because we took an inverse operation, so we're only going to get the positive outcome of the value. Remember, rad 27, when we did these before, right? This is equal to rad 9 times 3, right? So then 9, take a square root of is 3, comes outside of the radicand, and the 3 is left inside. This is actually a special triangle that we're going to find out in the next section, okay? Or maybe it's section 9.3, but it's in this chapter. And we'll deal with these a lot, where we have one of these, the hypotenuse will be twice the size of one of the legs. Okay, we're going to determine if the triangle is right, obtuse, or acute. And this is our last thing for today. And here are your side lengths, 10, 11, and 13. Okay, so step 1. Is this a triangle? Might not be a triangle. Make sure that we have to test, right? Is 10 plus 11 greater than 13? It is. Is 10 plus 13 greater than 11? Of course it is, right? 13 is greater. And is 13 plus 11 greater than 10? Well, of course it is, right? Both of these values are greater than 10, right? So what that means is yes, it's a triangle. So it's very difficult to be right, obtuse, or acute if it's not even a triangle, right? But this guy is a triangle. We're good to go. Now we have to investigate these 3. So gentlemen, I might get you with that at some point. So what we're going to do, we're going to do the smaller 2 sides, 10 and 11. Again, the legs are the shortest 2 sides. I'm going to be looking for you taking this note in class as I erase it right now. Okay. Is this equal to 13 squared? And the answer is, it is not. Because the question is 100 plus 121. And then we have 13 squared, which is 169. That is clearly going to be greater, right? Because 221 is going to be greater than 169. So back here, we have 3 options. If it's equal, then it's a right triangle. It is not, so it is not a right triangle. All right, that's what the Pythagorean theorem says. Instead, this is either obtuse or acute. Now, what it's saying is the legs are longer. Okay, I will demonstrate this to you using the hinge theorem when we get to class. But when the legs are longer, right, it means it's an acute triangle, okay, because it is effectively overreaching. Like if you were to take, a regular right triangle and extend one of those legs, then you're gonna have to open up, right, that hypotenuse and swing in one of these legs to make it acute, okay? If it is less, and this is the irony, because acute is the tiny one, when it's greater than, it is acute. If it is less than, it's obtuse. All right? And we'll discuss that again in class. Good luck.